Very good afternoon, all. I hope you are doing well and enjoying the doing of the programming and binary tree programming you have started. So last class, we have started talking of a binary tree and creation of a binary tree. This is what I have discussed yesterday. The conceptual process of creation, effectively reading an existing binary tree is what we discussed. And I tried to give you conceptual steps to try and think or make the logic for that. So just to recall that, those who have attempted, I'm sure they might have done something and might have some confusions. Just to recall what yesterday we have seen or what yesterday we have discussed was these steps that we have said that primarily we have mainly 5 steps. I think there is some let me just focus again. Yeah, I think it works better now. Yeah, fine. So this is what we have discussed yesterday, and these are the famous mainly 5 steps. And I tried you to ensure that you should think in terms of these things. I'm sure some of you have attempted that and done that. Most of you might have been able to do something, but let's revise and do now with the syntax. So let's say I have a binary tree as a node structure declared. So I may say binary tree star. If I have a node type struct name as node, then I can say node. But binary tree maybe if I say create. First thing, any parameters? If my all 5 steps, whatever 5 steps we have used, if all those 5 steps, they need something from outside to be passed as a parameter, they will become parameter. If they need nothing from outside, obviously, then I don't need. So I can see whatever steps I have discussed, all those could be internally done without taking anything extra. So no parameters are needed. Return type has to be there. So obviously I said here I am going to declare binary tree star root. And of course, I'm going to have root to be returned. So this statement will be guaranteed there to make sure that a tree is returned correctly. And from main, obviously, that will mean I will be giving a call root1, let's say equal to create and a parameter, no parameters. So this will be the call. So up to this fine. Now, if you recall, whatever steps we discussed yesterday, we assumed first node exists. If the call comes, first node or root guaranteedly exists. That we have assumed. If I want to relax this condition, maybe somewhere I have to think of a logic, or maybe in the main I can ensure that. But if call comes here, I'm assuming root exists. Root exists. So first step, malloc, that will mean root equal to typecasting and malloc. Second step, reading of the data. So I maybe say, I'll say printf, enter the data, so that I get a message that some data is to be entered. And then I will have the scanf for the corresponding root arrow data with proper syntax or a separate variable taken, etc., etc. So all that happening as a second step. Third step, I have to check whether left child, if left child exists, then I'm going to do the reading. So if left child exists meant what? Maybe I'll ask the user, is there left child existing? Does left child exist? For certain node, if I want to give, I can give a message based on the data. Otherwise, I can write this. If yes, so maybe you can say you press Y or N. Then accordingly, you can read a choice. And if you are giving percentage Y or N, then percentage C will be must. If you want to give 1 or 0, accordingly, you can have integer. If choice equal to yes, what to do? I want to read. Else what? Else I have to do something. I want to read. Choice equal to yes means read or create left subtree. That guaranteedly means a recursive call. Create. No parameters, hence the call is as simple as this. But by doing this, let's see now what happens. First step, let's say I gave step 1. Malloc done, root created. Step 2, the data being read. So this is step 2, let's say 30. I have read properly. Step 2 done. Step 3, does left child exist? I said yes. Yes, left child exists. At present, nothing done. I just asked for the left child. Now, as soon as I wrote yes, create function called. Create function will mean read a left subtree. Let's assume my left subtree used to be, let's say, something like this. Say I wanted to have something like this. So this create will guaranteedly read correctly and this root will be returned. This will be the root node. This will be returned by this call. This return to use where? This will be the next temporary root and this will be returned. This returned value has to be used. But by left subtree call, only this much has been completed. And assuming everywhere else we have done null, 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 all that has been ensured and everything like that, null always. So wherever we have, and all that thing has been done. This reading complete, this linking has not been done. This linking has to be done like this. Whatever is returned type, that should become this node's left. If once I have this, so the way will be simple. I can say root arrow left to be equal to create. Because currently my root means 30. Root arrow left to be assigned whatever new reading happens. Once a new reading will start, 40 and all that will be created, 40 will be returned, root arrow left. Else, for example, if 30 has no left child, that should mean I have to write root arrow left to be equal to null. And same process to be done for step 4 for the right child. So right child will also mean, let's say I have here data 80, 90, 100 and other remaining null. So this will be again returned with right side called. Whatever call to create you have given for the right child, that will be returned from here. And if that is returned, I have to say link this like this. So this effectively means root arrow right equal to create. So this is what I have to ensure for the right child also and similarly for the left child also. So if I see now, based on my logic, which I have just implemented, the same thing we have done, and finally the root will be returned. So you can always assume that this call works correctly recursively. And similarly, the other call also works correctly for the right child also. In that case, your rest of the logic must be ensured to work correctly. Then the function will be complete and code will be ready. Just to have a demonstration of this, we can have the corresponding function code shown to you into the dev CPP. So let's have a code here. Let's say I have node or binary tree, whatever structure you declared. In order to check whether the tree has a root or not, maybe I say I want to give an empty binary tree, then I can ensure that checking into the main itself. So you say if the root has root or if the tree has root or not. If yes, then I will be calling the create function. Otherwise, I will say simply root equal to null. And if this is there, the create call comes. How create function works? Malloc, first step. Second step, data reading. Third step for the left child. If the left child exists, before going for this I have given F flush because last classes we have discussed you might have pressed enter after reading this data, let's say 30, and then you have pressed enter. If you don't give F flush, enter pressed after 30 will be creating a problem for this scanf and have a certain issue. So I cleared my stdin file and now I will be able to read the symbol. If choice is yes, then I will be giving root arrow left equal to create, else root arrow left equal to null. After pressing Y or N also, I will press enter. That enter will not be problem because next time in next iteration, integer will be read. So enter created is not a problem. So no F flush is compulsory before this scanf, but before this scanf, this F flush is compulsory. Similarly, to be done for the right child, does it have right child, F flush, scanf, and then accordingly create. So this is how it is going to be coded and used for this situation. So having said that, now you have easily seen the code. Let's understand how does it really work at the internal level. So if I have implemented this first time when you called, let's say you said root exist, step 1, malloc done, step 2, 30 assigned. Then you said, is left child existing? Yes. Now what happens? Left call meant immediately, meaning that this function again started. Create function again started. Recursion starts. Recursion starts again means again it gives a malloc. Again malloc means another node created. Enter data, let's say 40 entered. 40 entered, again asked, does left child exist? I said yes. Again, recursion starts. Immediately based on the choice, this recursion starts. And recursion start means again malloc, again 50. Done. 50 done. And after this, 50 is allocated, then again asks, does it have left child? I'll say yes or no. If it said no, no meant you went to this statement. This statement executed and this became null. Then you asked, right child exist or not? I said no. This also got null. And now return root. This pointer returned for the first time. So this is the first node which is getting completed and returned. As soon as you return, previous recursion resumes. Previous recursion was here, and that also for the left side. So this resumes. Resuming means now this statement works. Root arrow left equal to returned node. For this particular recursion, this is my root. Root's arrow left to be equal to returned pointer. So this is the first time linking established. Create function over, else ignored. Similar process for the right to be done. For the 40, right child exists? I said yes. Yes meant again a recursion for the right side. For the right side, again recursion started, again went up 60 and node created 60 read. 60 read, does 60 has left child? I have yes, I want to give 70 also. Again Y means again recursion. Again means again recursion, 70 created, 70 stored here. And now 70 is left child to be null. 70 is right child to be null. Return this node. This is a node being returned. Node return means recursion resume. Because previous recursion over, this recursion based on the stack, the last recursion resumes. Lot of recursions are pending, but this recursion resumes. Resumes means now I have here a statement 60's arrow left was being called. This statement resumes 60's arrow left, this linking down. So this linking established. After this, it says, does it have a right child? Means this 60 has a right child. No. So I will give here null. And now 60 is returned. 60 returns means previous recursion resumes. Previous recursion means 40s or this node's right to be assigned this link. So this link established. And after this node being returned. This node returned. Here this recursion resumes. So this recursion with the left was already there. And here recursion for the left was pending. This will be resuming. This link established. Again, this side, yes, means again now recursion for the right is pending. And again, let's say 80 will be read. After 80, 90 will be read. So I have 90 read. After 90, 100 will be read. 100 will have everything as null. And this link will be established now. After this, 190's right child, that will not exist. This will remain null. And now this link will get established. 80's left child was already null. So this side has been already null. Now this will be returned and this link will be established and this root will be returned. And this is returned finally to your main. And this will become your created tree. So this is how internally it will work. So internal steps should be clear to understand how it works for the recursive calls. So now let's try to see, I want to give the same input in my dev CPP. So 30 has 40, 50, 60, 70, this tree again to be entered. So I'm just drawing it and I will be having the same as input to be given. So let me just again go to dev CPP and here is the code. Let me execute it and show you how internally it works. So now my execution starts. Does tree has root? Yes. I said data to be entered, 30. Now, based on 30, does it have left child? Yes, 30 has a left child. I wanted 40 to be its left child. To be precise, I'll just show what tree I am inputting. I will keep it here and keep that screen also active for the time being to show you what tree I am inputting. So tree, this is being input, and now I will keep my screen, this window also active parallelly. Let me have this minimized, and along with this, I have this. So now I can easily see that both screens are parallel. So effectively, I am trying to input 30, then 40, 50, etc. So does this have left child? Who? Current node always. So 30 is being asked. I said yes. 30 is left child to be inputted, meaning that effectively I will be entering 40. Does it have left child? Yes, I'm talking of this 40 is left child. Yes, it has left child. So I said yes, 50. Does 50 have left child? No. 50 has right child? No. Now again it asks, does it have right child? So as an input provider, I have to understand how recursion is working. Only then I'll be able to give input. 50 is over. Previous resumption with the 40 node continues. This node 40 resumes. 40's right child is being asked. So I will give here, yes, I want 60 to be its right child. 60 is right child. Of course, a 60 is left child being asked. I want yes, I will give 70. 70 is left child, no. 70 is right child, no. And now I say again it asks me left child. 70 is over, 60 is over, 40 is over. So now it is asking, sorry, I think I pressed some wrong symbol. So maybe fine, no problem. For the 70, I said right child, yes, by mistake. So I have given some data. Then it says, does it have left child? No. So I'm talking of 70s left child. I'm talking of 70s right child. Nothing being done. 70 over. Now it again asks me right child. 70 over. 60s right child is being asked. You have to resume. 60s left child was there. 70s over. 60s left child. I say no. Again it asks right child. 60s over. 40s over. 30 resumes. 30 is right child. I say yes. 80 being input. After 80, 80 is left child. No. 80 is right child. Yes. That right child is 90. So 80 is right child is 90. 90 is left child. Yes. 100. 100's left child. No. 100's right child. No. And then it says again a 90 is right child. After 100 over, resume at 90. 90 is right child. No. And then after 90, again, I think there is some call pending. So accordingly, that now you can see it's very difficult to remember and trace and make sure that we are not having anything wrongly inputted. So now again, after this, again, it will resume and we have to accordingly keep on giving all data in that way. So it gets over. So this is how it will internally work. And now based on all that, we have to really remember all these things. But knowing this is how it will work internally. So of course, I would like this message to be in a better manner. So improvements into the create are possible, but otherwise create is definitely working without much of a difficulty. So let me just continue my discussion now that create understanding or create works well, not an issue at all. Let me just have this. So create, okay, but user interface or user message, user gets no idea. User has to know how internally recursion is working, where recursion resumes, and then accordingly I have to give the data. So there can be meaningful messages to help me. So I can think of improving create to have something like this. That I'll talk a bit later. Then I assume that once I have understood this, let's have the traversal. So once creation is done, binary tree has 3 standard traversals. One is called as in order, other is called as a pre-order, and third one is called as post order. As the word suggests, they tell how they will work. In order means all these talk in pre-post with the reference to the root data. So in order means roots data will be inside. Left will be always first, right will be always after left. So in order means left subtree fully, right, and then data to be in order, and then right subtree to be traversed. On the other hand, pre-order means node, that is root to be D, and then left, and then right. Post order obviously means left first, left and right. Out of these, left will be always first, right will be after this, and post means data to be at the last, post. So it is called as LDR, it is called as a DLR, and it is called as LRD. Here data is a in order, data is a pre-order, data is a post order. For example, if I say that my tree is 30, 40, then I had 50. So I'll just use the same tree which we have just drawn, and I will continue to use the same again. Let me just keep this side. So I had 30, 40, 50, 60, then I had 70. This side I had 80, this side I had 90, this side I had 100. So in order means 30 should be in between of left traversal and after 30th should be right traversal. So left traversal doesn't mean only 40, because left traversal means whole left subtree to be recursively applicable in order to be applied on this node also. So the same definition, traversal is also recursive definition. This means left subtree, right subtree, or left traversal, right traversal. So traversal itself, using a traversal over left, traversal over right, will mean for 40 also the same logic applicable. 40 will mean 50 followed by 40 and right side. For 50 also same applicable, for 50 left side and then 60 and then 50 and then 60. For 60 also this. So effectively it means whole left traversal followed by 30 followed by right traversal. Now, what will be the output we will understand, but before that let's have the implementation. Implementation will be very simple. It's a recursive implementation. Void in order. Definitely I need some parameter now. For example, binary tree star or node star root to be passed. It has a recursive call for the left traversal, a recursive call for the right traversal, and this data is a non-recursive, a normal printf. Obviously, recursion means it has to be based on the if condition. It cannot be unconditional. So if the root is null, obviously there is nothing to be displayed. So you can write if root equal to null, return, or you could say when to call recursion. If root is not equal to null, only then the traversal has a meaning. Otherwise, nothing else to be done. So either you write root equal to null, return, or you write if this and then statements inside. If root not equal to null means traversal to be done. LDR. LDR means left traversal first. Left traversal. Traversal recursively called means in order to be recursively called. So I will call in order with root arrow left. Left traversal means this is an in order traversal over the root nodes. Similarly, next is data to be printed. It is a non-recursive call, so it will be printf %d and some space. If you want to print, you can print a root arrow data. Then what next? Right traversal. Traversal means in order function call, and right side means root arrow right. So traversal becomes very easy and function over. Similarly, we can see for others also. For pre and post also, it will be the similar process. But before we go, let's see what output we will get and in what way. Start with this root, say in order traversal started. 30. As soon as root is not null, you call in order. Again, a recursion means go back. And I say this is a recursion resuming, and I'll say this recursion is a pending for the left side. For the left side call generated, and now I am going there. Let me just shift it here. So call resumes and I start with this node. This is my current root. Root is not null, so recursion starts. Root recursion means again in order call. Again means this in order call will means this become pending. So this node becomes pending for the left side call because there are two calls. So I'm noting for the left side. Recursion comes to this node. 450, again a recursion started. 50 is not null. 50 not null means root in order again called. Again called means I reach to this side null. Recursion with this null is called. This is my current root. I go to in order, root equal to null. I simply reach here, function over. This function over, recursion is over. I reach back to this node. This is my current root. Now, first time root arrow data is printed. I am on this node. So first time 50 is printed. After printing 50, in order root arrow right. Now, from this node, again, recursion is pending for the right side. For the right side, we go with this node for 60. Again, recursion starts. Root not equal to null, yes. In order root arrow left. Again, this recursion becomes pending for the left side. I come to this node. 70. 70 is again not null. 70 is null left side, and that recursion starts. Recursion starts, root left will be null, nothing will happen. This data will resume. Recursion will go there and get over. Again, you go back. Now 70 gets printed because of this. And then recursion call towards right side. Right side call generated, root. This time now this will become root. That will be null. I'll come back. 70 is over. After this previous recursion to resume. So this recursion resumes. This recursion was for the left side. Left side over means after left side a data printed, 60 printed, and recursive call to the right side. So recursive right becomes pending now. For null, nothing will happen. Recursion back. Recursive right resumed. After right, there is function over, again goes back. Now, the 50's right side was pending. So this pending was over. Again, I go back. Right side over means just over again. And now recursion for the left side for the 40 was pending. Left side call has been completed. Now 40 comes. 40 comes. After this, 40 is right side. Again, there is nothing on the right. So 40 will be over. You go back to 30. So now this is your left sides in order. And this data has been printed. Then you have this data of the root. So left side was effectively recursively applied. The first node being printed was 70 as the leftmost, then 60 its data, no right. Then this whole is a right of a 50. So 50 was the first to print, 50, and then followed by 60. So this became a 50 nodes traversal. This became a 40 nodes left traversal. 40 has no right side, and then this data. And now recursive call will come for this traversal, right side. Out of this again, from 80, first left side, no left data existing. So that will mean LDR, left over 80 printed. After 80, recursion comes to 90. For 90 also same LDR applied. So 100 is on its L. 100 has nothing more. 100 printed. And once you have printed 100, after 100 printing, then you have the corresponding 90 printed. 90 has no right child. So my overall display will become 50, 70, 60, 40, 30, 80, 100, 90. This will be my in order traverse. Then similarly, I can think of doing a pre-order. In pre-order, what will do? Printf to be first. And then pre-order to be recursively called for the left side. And pre-order to be recursively called for the right side. And of course, if etc. needed, so this becomes a simple pre-order. Similarly for the post-order. Why do I need 3 traversals? Because none of these traversal alone is going to be unique. For example, there can be 2 different binary trees which will have same in order traversal. How? Let's have a look. Let's say I have some data 30, 40, 50. It's in order means what? It's in order means 40, 30, and 50. Perfect. But there could be another tree in this form where I say, first of all, 40 should come, then 30 should come, then 50 should come. It's in order. If you see left 40, then data 30, then right, nothing applicable. For this node also, left is over, and then data, and then right, nothing available. So both have same in order traversal, although trees are different. But if in order is same, the pre-order and post-order will differ. For example, it's a pre-order. Pre-order means LDR, DLR. D means 30, then it's left child or left subtree, then right subtree. It's a pre-order. DLR. DLR means always a data first, that means a 50, then left side. For 30 also, data first, then left side. 40 also, data first, and then left side. And so you can say the pre-order here is different, pre-order this. So we will require all three traversals to be checked. So always do all three traversals or at least two traversals in order and pre or post. So always check your tree linking, etc. and tree's full structure or full shape using three traversals. That will ensure that you have created it the way you want it. And verify manually whatever output you are getting with your equivalent in order pre-order traversal, so that you will be sure that you have created a binary tree correctly. Well, having said that, now let's see how recursion will be used for various operations. So we are going to use binary tree for lots of operations, but obviously you might have a question, why binary trees? Why or where used? Tree you have read in file system. We have said file system storage, etc. is via trees. What are applications of a binary tree? There are lots of applications. To be precise, let me give you a simple case. For example, when you say b square minus 4ac, you wrote in some expression. This expression needs to be evaluated using board mass rule. But at OS level, at compiler level, this board mass, how it is applied. This for binary operators or for binary such expressions, binary operator based expressions, or similarly, we will have a binary tree for this expression made. And that will be used to do the evaluation. For example, it says minus is to be applied over b square and 4ac. So minus will come in between and it will have its left operand this side, right operand this side. Recursively same definition again applied. So you have here operator and you have here left operand and here you have right operand. That will indirectly mean b square also to be applied recursively same definition. It will mean star coming in between, b becoming one operand, b becoming another operand. 4ac. 4ac means 4 star a star c. Out of this also, 4a gets calculated first because we know left to right associative will ensure 4a getting calculated first and then c coming here. So this will mean star coming here, this side 4a and this side c. 4a again means multiply coming here, this side being 4, this side being a. And it's in order traversal now. In order traversal. In order traversal will ensure the equivalent binary arithmetic board mass based calculation. LDR, from here left side, from here left side, B into B. So your evaluation will happen LDR, B star B calculated, ready. Then comes minus. Now, right side to be LDR, right side, star. Star means again LDR. So star means again L. Star means again L. This has left nothing more. 4 LDR. 4A over this star now, D. And then accordingly C also. LDR. So all this gets calculated via in-order traversal and it will be ready. So there are many such similar more applications of a binary tree. So let's see now how to have operations implemented. Implementation, again, as you can smell, mostly recursive and easy. Non-recursive implementation will be much more difficult. For example, let's say I have a tree like this, 30, 40, then I have, let's say 50, I have 60, I have 70, I have 80, I have 90, I have 100. So corresponding to this tree, now I want, this is, let's say, root 1. I say copy a binary tree. This operation to be implemented. Meaning what? Meaning that generate a new binary tree with the same shape. Exactly same shape. Meaning what? Effectively meaning that both will have same traversal. All three traversals, not only one. How to do that? Effectively, it means I should be able to have another root 2 where this is 30, this is 40, and this is 80, and so and so. So this should be copied. Like copy a file, copy an array, copy a binary tree, copy a linked list. Now, try to think over this and try to make logic. And logic, obviously, if you are able to make a recursive definition, things will become much more easier for you. So, first thing is, the copy itself means I will have a copy function. For copying, I will need some parameter. So, for example, root 1, I should be able to have. And what it should be return type. The copied string, tree should be returned. So maybe you say node star or binary tree star, whatever you say. Because in my programming, I have showed node star. So I'm just using the word node star. And maybe new root will get calculated. So if I say, let's say copy root with the syntax I'm calling, ultimately I would like to write here return new root. So a new node should get, a new binary tree should get created, and that should be returned. And in main, my call will be something like root 2 equal to copy root 1. And then I should be able to use this, and then in order, pre-order, post-order, traversal over root 2 should give me all same output which root 1 was giving. This is what I have to ensure. How to do that? So think of the logic. I say, think recursive definition for copy. Make steps. Step 1, 2, 3, 4, whatever. And of course, they all will be conditional. Recursion cannot be unconditional. What should be the condition? Yes, you are right. You can think easily. Think over this recursion condition. What should be the condition? So condition is obvious based on the null pointer. So whatever syntax you wanted, obviously you will put that. And if root is equal to null, what to do? Root equal to null means nothing is to be done now. And we have effectively null to be returned. So you can write return null. Of course, other alternate could have been you could write new root equal to null, and then later you will do the return null. Otherwise, this also will work well. Done. If you reach here means the tree is not empty. Not empty means you have to copy and make the whole tree duplicate. Think of the logic, give a pause to the video and try to write the steps. Once you are able to write some steps, you might have certain doubts, might do something, and then I'll explain what is missing and what is to be done. So give a pause here. I'm giving few seconds pause, and then you can resume and replay the video. Over. Yeah. So I hope now you are ready with the solution. So I say, solution how to do. I'll say, my step should be, this was my root 1 or root. So I'll say first step. I have to create a new root. So I'll say create a new root node. Which is the same as the root node. If I want to do that, how to do? Effectively means same as this means this node is called as a new root. It has data 30. So how to do that? Effectively, this step means it has a 2 steps. So I'll say first step is obviously malloc and second is the data. So I'll say if the condition is true, first step is new root equal to malloc. And second step is new root arrow data. To be equal to what? Root arrow data, obviously. Yes, perfect. Now, third step. Recursively, if I can think only, then things will be easy. Otherwise, you think, okay, I will go non-recursive. Like I have this tree. So first I will have 30 copied. Then I will make 30 arrow link equal to another node 40, another malloc. 40 arrow link equal to 50, another malloc. 40 arrow right also to be another malloc. 60 arrow left to be 70, but 60 arrow right not to be given malloc. 80 is left not to be given malloc. 90 is right not to be given malloc. Iterative logic will be really difficult. I say my logic could be as simple as that I will say after this, I will claim whatever was its left subtree, same to be copied via copy call. Meaning that whatever this left subtree was gets copied directly via this recursion, and my work is just to link this. My work is just to link this. So coming here, I said my first step was malloc, new root equal to malloc. Then a new root arrow data to be equal to root arrow data. That was the second step. Third step, copy left subtree. Copy left subtree means a copy call. Left subtree means root arrow left, because this is the subtree now. Copy left subtree and then link to be done. Already this kind of a linking we have done while create also. Exactly same thing we have done. So effectively meaning new root arrow left to be linked with this side. Done? Simple. And similarly, the fourth could be new root arrow right equal to another copy call. And then finally return a root. So effectively, this becomes the fifth step, and that's it. So primarily, it has main three steps: your data or root being copied, then left subtree being copied, right subtree being copied. In traversal also, we had the same logic: root being printed, left subtree being traversed, right subtree being traversed. So it's a recursive call, and one step is non-recursive. And then in this case, I need additional return also. If root is null, obviously I'll stop. Simple logic, not a difficult logic at all. I say some of you might have thought in a slightly different manner. For step 3, you might have thought that I should check whether left is null or not, like in creation we did. So yes, that's also perfectly fine. If you checked if root arrow left not equal to null, only then I should call this function, or only then I should go for recursion. Still it is perfect. New root arrow left equal to copy root arrow left. Yes, perfectly fine. Else what to do? Whenever you write if, don't forget to write else. Else what will you do? Root arrow left not equal to null meant that obviously here I will say new root arrow left to be equal to null. This step is also equally good, similarly for the step 4 also. This is also perfectly okay. So I say, if you see the previous step versus this step versus this, both are identical, and I say there is absolutely no difference. You can write like this also, but you can also write like this also. This will also be okay, and it takes care of null also. How does it take care of null? You should verify that. In this case, for left not equal to null, the call is the same, not a problem. The only difference is if root was null, here I have a non-recursive call. Will this be equivalently done via this? Let's see. If let's say root arrow left is null, null means a recursion called here with this being passed as a null. If a recursion call comes here with null, immediately it will mean a root equal to null, return null. So this call, when I wrote new root arrow left equal to copy root arrow left, I wrote this call. This returns, if this was null, it will return null. And hence, this statement means exactly equal to null. So this statement is exactly equal to this statement. So without if also it is perfectly fine. With if also it is perfectly fine. And extra if doesn't make any time complexity loss also. Hence, time complexity will also remain similar. Few 2 or 3 lines extra will execute here without recursion. Via recursion, the same number of statements will work in the next recursion. So more or less step count will also remain similar, and hence all complexity remains similar. So this can be a fairly simple way of handling this. So with this, I think we are going to close the discussions today, but the only one thing I'll touch upon before we close down, and that is what I told was creation improvement. I was not able to create easily when I executed because which recursion was assuming I could not. Secondly, simple improvement can be you can use a double star also. So I can have a void, create, and star root. So I can say let this becomes a create 2. This can be one improvement. Try this. Instead of having node star return, void star create 2. Then I say, so create 1 was, which I have done already, and this was returning node star. That was create 1. You have already done. Create 2 can be this. Then I say a better will be create 3 with meaningful messages. Yes, good students should try this. I mean, whenever the message came, I should get a message, does 30 has left child? Have left child? Or I should, whenever the where earlier, or no, I'll say not does 30, I'll say earlier the message was enter the data, but enter the data never told which data I'm talking. If I get a message, enter node 30's left data child, or I get message, enter node 30's right child, then the message will be meaningful. So printing can become meaningful, but whenever the focus was on 30, then I need this message. Later I reached to 40. I should get the same concept now. I should say enter 40's left child, and then I will give 50. Similarly, that logic continue. Later, whenever ready, then I should say 40 is the right child. And then I should say 60. So this should get 60 read here. But remember, my function is calling from this node now when I'm calling for 50. And that time I need the parent's data and which side. When the reading is being done, this call is coming reading or recursion on node 40. At that time, I need this message. My recursion has reached to, let's say 30 has been read. A recursion call comes to this node. This is your root allocated. 40 is to be read. And now I want a message, enter 30's left child. So I need certain data to be supplied as a parameters. So effectively it means the parents data and the direction, the side, maybe left or right, should be known if I want this logic to be implemented. So what I need here is that whenever the create function is coming, create 3 can be implemented by supplying here the parents data and let's say 1 or 2, where 1 means I want to read the left side's data, 2 means I want to read right side's data, And accordingly, your printf message takes care of printing this data. Enter 30s left side or right side. And then accordingly, I give this message, and then rest of the program remaining similar. So that can be the changed function. So my node star create 3 can be made to have like this. Of course, there can be other ways also for doing the similar work, but this is one of the way which you should try. So parameters will be used here, and good students can think of implementing this logic also. Those who find it difficult need not bother, because create 1 and create 2 still work fine and without difficulty. Then, so my homework, number 1, create 2 must be tried. Number 2, I will say, using recursive functions only, find max total number of nodes in the tree, find count of nodes in the tree. In the binary tree. This is second. Third, I will give find max out of all values of the tree. And similarly, instead of a max, you can find min also. But for these functions, no global variable to be used, no static variables to be used. Some of you might think of using some global or static variables. No global or no static variables. The recursion will become only clearly understood if you try without global and static. So recursion clarity should get developed. And once you are able to get that recursion clarity, implementation of all these concepts will become such an easy work. Try this, and this should be your homework. Practice problem I have already given, which is optional problem for good students. That is, create 3 functions with meaningful messages. To read the data. So if you can try this, that will be even good. With this, I think I'll stop here. Bye-bye. All the best to all of you.